Welcome to my Cisco's Scaling Network class. Here we're looking at Chapter 2, LAN Redundancy. So in this chapter, we're looking at key technologies for redundancy and for redundancy like loop prevention. So we're actually going to start talking about loop prevention and then get into redundancy. So it's just kind of interesting because this chapter kind of was done backwards. You're going to notice certain technology, which previous used to be in the CCNP level, is now dropped down to the CCNA level. For example, first hop redundancy protocols. So without further ado, let's go ahead and get into some of our spanning tree concepts. So first of all, we have to understand what STP or spanning tree is, the different types of spanning tree, PortFast versus rapid, versus other major common issues with setting up and configuring STP. We're going to discuss kind of what first hop redundancy protocols are. We're going to be looking at mainly HSRP and GLBP. Again, HSRP was one of the big first hop redundancy protocols that you would use in the CCNP level switch course. So this has been kind of lowered down in the CCNA again. All right, so our first major one is spanning tree concepts. So what is spanning tree? So normally you can have redundancy at both layer 1 and layer 2, at the physical layer and the data link layer. So you can provide physical redundancies into a switch network. You can do that by having multiple links to multiple switches. This again would then in turn improve performance, reliability, the availability. It allows higher utilization of or higher access to some of the network resources and possibly could have higher utilization of bandwidth, because if you have multiple links when you're trying to access big data, then you have multiple ways to get that big data across that network. So got to keep that in mind. So when we're looking at redundancy, MAC address instabilities, broadcast storms, and multi-frame transmissions, as well as frame size concerns. Right now, we've been assuming that frames are going to stay the same 1500 MTU size, but that's not always the case. Sometimes you can have jumbo frames. So there's some considerations when talking about redundancy at the layer 1 and layer 2 levels. So let's go and look at some issues with the layer 1 redundancy. One of the problems is you might have MAC database instability because again, Ethernet frames do not have a TTL, so frames continue to propagate between switches endlessly. So one of the problems is you may have multiple paths to a single MAC address, so that creates some instability. So errors can occur due to broadcast frames being forwarded. That's a big one. So what happens when you have, I'm going to try to do this with a pin. Oh, that's not what I want. Pin. I know they're circles, but we're just going to pretend they're switches. What happens when a broadcast is sent from one switch to two other switches? What will happen is a broadcast will be forwarded out all ports that it was not received on. So it will not, for this one, it will not be sent out that one, but it will be sent that way. This switch will not send the broadcast that way. It will send it that way. Well, that's one. Two, this switch will then get the broadcast from the lower switch. It will not forward it out that port, but it will forward out that port. You start seeing where this just became a giant loop, and all the switches are forwarding the same broadcast frame between one another, and this in turn consumes more and more resources because again they're having to process more and more broadcast frames that was originally sent from one switch. So what we're talking about is actually called a broadcast storm. And again, that's when there's so many broadcast frames caught in a layer 2 loop that all available bandwidth is consumed. Normally known some type of a denial of service type attack, not a distributed denial of service, because we're not really distributing that load to attack something. It's more of a, sadly, error. So broadcast storms are inevitable on a loop network because, again, there's that giant loop. The more devices sending broadcasts over the network, the more traffic that's caught in the loop, and then, again, so forth and so forth with resource management. So issues with layer 1, here again, we may have there we go. So this could actually, if this starts the broadcast, or this PC starts the broadcast, it will be forwarded out all ports. And that becomes one of the problems. Is because up here, we're going to have this giant loop, and it is going to start just consuming resources. So duplicate unicast frames. When a unicast frame is sent into a loop network, it can actually have duplicate frames arriving at different destinations. Most upper layer protocols aren't designed to cope with this. So layer 2 LAN protocols such as Ethernet typically lack a mechanism to recognize and eliminate these endless loops, so something had to be done. Here we go. This is an example of duplicate unicast frame. So switch 1 MAC address for PC 4. It realizes it's on port 3. Here PC 4 is on MAC 1. And I mean, you can just see how the MAC address for PC 4 is going to be on different ports. So what had to come into play was something that would prevent these switching loops. So spanning tree was introduced, and it uses a spanning tree algorithm. So spanning tree protocol ensures that there's only one logical path between destinations, thus preventing loops. So typically ports will be in different modes based off of a criteria that is done to prevent loops or to prevent data from entering or leaving a specific port. So what ends up happening is we have what's called a Bridge Protocol Data Unit, a BPDU frame. This is what is sent to prevent loops. This will be sent out all ports, even if ports are deactivated. That way, we can verify our actual connections in our network. So the physical path may still exist, but logically, we can control some of the links being up or down. So here, we have a link between switch 3 and switch 2. Switch 2's port F02 could go into a temporary shutdown mode, even though the physical link is there, because STP detects a loop and says, hey, this path is doing a loop, let's go ahead and turn it off. And if, for whatever reason, the link between switch 2 and switch 1 ever goes down, it will automatically turn back on the link between switch 2 and switch 3. So switch 3 may receive the frame and forward it back to switch 2. Switch 2 should drop the frame because, again, that port is in a blocking state. So we end up is the different types of port roles. So first thing you have to realize, 3 very common port names. You're going to have to understand what a root port is. Was it designated port is and a designated a non-designated port is. So a root port is going to be the port going towards the root bridge. The root bridge is elected, and it is going to be the main switch in a switched network. That way, you have one device controlling Spanning Tree Protocol, or STP. The ports heading away from the root bridge are in what's called a designated port. The ports that are going to be shut down will be called non-designated ports. A better definition may be a root port is the port that always links back to the root bridge. A designated port is one that has determined as having the best or lowest cost. A designated port will be a forwarding port. When we look at this, so this link going towards the root bridge, those are going to be the root ports. The ports going away from the root bridge will be the designated ports. So the root bridge, well, how does that become a root bridge? So first thing is we're going to be looking at a bridge ID, which is normally a priority ID. Normally, it's going to be the lowest priority should get the root bridge. So the bridge ID with the extended system ID would be the bridge priority, the extended system ID if there is one, and the MAC address. So again, here the election will take place. We will have switch 1 with the lowest priority become the root bridge. And then next, we're going to start calculating paths. Well, the problem with that is, what link are we going to shut down? Are we going to shut down the trunk 1, trunk 2, trunk 3? So what we have to do is we have to figure out the total cost to get from one device all the way through. So for example, path 1 from switch 2 will be switch 2 to switch 1 out FA01 to switches 1 FA01. One link. That's going to probably be a 100 megabit connection, hence the 19 cost metric. One link at 19 totals 19. So if we want to go the other route, this route, we have 2 links at a speed of, or a cost of 19, that becomes 38. So this path is the longest path, thus should be, one of these links should be shut down. That way, we can use the shortest path. Happens to be the path between switch 2 and switch 1, so that one will be good. So we'll be looking at either the link between switch 2 and switch 3, or between switch 3 and switch 1. It will actually turn off one of these ports. And again, there will be a portion of that election that will disable one of those ports. That's more in depth for one of the later discussions in Spanning Tree Protocol, but recognizing that one of these links we turned off is the key at this level. So let's go ahead and look at the BPDU frame format. So if you're able to capture the frame, this is what it's going to be looking like. You'll notice that it should have a destination for a spanning tree. The LLC should show spanning tree, and it should actually be able to show you BPDU configuration types, path cost, bridge identifier, MAC address, all of that detailed information. Route path, route identifier, bridge. So the BPDU propagation and the process. So let's assume we have a simple network, 3 switches. We have a route ID. We have a bridge ID. And we have a path cost. So switch 2 will forward the BPDU frame out all switch ports. The BPDU frame contains the bridge ID and the route ID for switch 2. Because when you first get turned on, all switches are the root bridge. So they have to do an election process to figure out who is going to be the root bridge. So at first, they all think they are the root bridge. They will, once they get turned on, they will send a frame that has their ID and, well, their root ID and bridge ID and the associated costs between one another. Thus, that starts the election process. Here we're looking at a root ID, priority ID, plus the MAC address. And if we're looking between switch 2 and switch 1, it's going to see, well, who gets the priority. So switch 2 will compare the received root ID and its own and identify switch 1 as the lower root ID. So switch 2 will update its root ID with the root ID of switch 1. So S2 will now consider S1 as the root bridge. It has the lower number. So what is this extended system ID? That's going to be the bridge priority and the MAC address. You can also have a bridge ID with the extended system, which would be bridge ID, the bridge priority with the extended system ID. So this was done to enhance areas for VLANs. Basically, it allows us to do a VLAN ID, to it be included in the BPDU frame through the use of the extended system ID. That extended system ID, VLAN numbering. So here we have, again, our bridge ID, priority, and a MAC address. So the priority of all the switches might be the default 32.769. The value is based on the 32.768 default priority. So VLAN 1 assignment is associated with each switch with the default plus 1, 69. 327.68 plus 1 would make it 327.69, hence the VLAN. If we were doing VLAN 10, it'll more than likely be plus 10. That's going to be the bridge, or the extended system ID, sorry. That way our bridge ID can reflect the appropriate VLANs. So, is there more than one type of VLAN? Area 2 is all about the different variations of spanning tree protocol. Common ones are STP, or commonly known as IEEE 802.1d, that was the 1998 build, PVST plus 802.1d, the 2004 version, Rapid Spanning Tree, also known as 802.1w, Rapid PVST. What does PVST stand for? Per VLAN Spanning Tree Plus, or my favorite, Multi-Spanning Tree Protocol, or MSTP, also known as IEEE 802.1s. If you want to know more about multi-spanning tree protocol, I did a video for my CCNP switch class. I included in a playlist on spanning tree protocol, but it's an in-depth, detailed 2-hour video about the very beginning all the way through multi-spanning tree protocol. Great video, but it's a timely one. So what are some of the varying characteristics? Is, again, like PVST plus, is a Cisco standard, not an IEEE standard. MSTP is Cisco and an IEEE standard. Resource utilization. STP is low, PVST plus is high. You guys can go through the chart. The important one here is the convergence time. How quickly does it converge? So you're going to notice that the slower converging ones are going to be STP and PVST plus. We're probably not going to be using those. We want fast convergence time. So things like rapid spanning tree or rapid per VLAN spanning tree are going to be important. But you're going to notice, again, utilization of resources. So rapid spanning tree is probably going to be pretty common. MSTP is also going to be really common because, again, they're both fast converging and their resource utilization is medium high, where rapid per VLAN spanning tree is going to be very high. So got to keep that in mind. Next, the tree calculation. What is going in with that? Rapid spanning tree protocol takes into account all VLANs. Rapid per VLAN spanning tree is specifically individual per VLAN. So not all VLANs, but it's going to be done per VLAN. So you can actually do separate root bridges off of individual VLANs. Where MSTP is going to be per instant. MSTP is a CCNP level conversation. But again, I've already done the video on that. If you want to know more about it, check out that video. So again, PVST, normally it's going to have very specific characteristics. It's optimized for load balancing. One spanning tree instance for each VLAN. And this is going to be maintained. And so this does mean a considerable waste of CPU cycles for all the switches in the network, in addition to the bandwidth for each of the BPDUs. We may have 3 VLANs, so we're actually going to be doing 3 root bridges for the all the different VLANs. Port states are going to be another interesting conversation because when it comes to spanning tree protocol, a lot more time needs to be spent on this slide alone. Port states: blocking, listening, learning, forwarding, and disabled. This is going to be an area where we need to understand these different port states. All right, so we're going to go blocking. Blocking state, it puts the port that would cause the loop if it was sending data, so it's the only one receiving the BPDUs until the topology change. It changes it to a blocking state, disregarding or blocking ports. Listening. Listening will process BPDUs and build the active topology. Learning. Learning builds the bridge table and no forwarding of data. Forwarding sends and receives data. It's a normal operating port. Disable will be a port that is manually isolated from the network. So, ports that will actually process and send forward data is forwarding ports. So the process for STP, here we're looking at specifically PVST plus, but I mean this is a common process. It will process the received PDUs. All of them will process the BPDUs. For data, that's only going to be the forwarding port. If we're looking for forwarding frames to another interface, again, that's only going to be forwarding. If we're looking at learning the MAC addresses, both learning and forwarding will be able to build tables. But again, remember, learning does not forward data. It only learns information. No forwarding is allowed. So again, in PVST, the environment, the extended switch ID ensures each switch has a unique bid for each VLAN or bridge ID, bridge ID. For example, VLAN 2, you take the default 327.68 and you add the VLAN number. Here we're adding 2, hence the 32.770. So let's talk about rapid per VLAN spanning tree plus. Again, all of these are preventing layer 2 loops, but with rapid PVST, it's an independent instance of rapid spanning tree, but it runs for each VLAN. So RSTP supports a new type. It's called an alternate port in a discarding state. There are no blocking ports for this. So RSTP defines port states as discarding, learning, and forwarding, even though the 5 states that we just learned are the common ones that are normally tested on. RSTP, also known as 802.1W, supersedes the STP or the default IEEE's 802.1D while retaining its backwards compatibility. RSTP, Rapid Spanning Tree Protocol, is newer. That's all that really means. RSTP keeps the same BPDU format, except the version field is set to 2 instead of 1. Again, here we have root ports, designated ports, and instead of non-designated ports, we're going to call it an alternate port. They keep changing the names, but the concept still stays the same. The alternate port will be the port that's disabled. The RSTP BPDU flags are here. Protocol IDing, protocol types, flags. Here, under flags, we may have 1 byte of data. And what does the bytes refer to? Topology changes, proposals, port roles, what we're going to be designating those ports as, and states, learning, forwarding, agreement, edge ports. So what is an edge port? Edge ports will never have a switch connected to it, so the immediate transmission to forwarding is a little bit better. So rapid per VLAN spanning tree protocol, you can actually set it so that these edge ports will not have to go through the learned state. What you can do is you can do it, issue a command called spanning tree PortFast. That will allow these edge ports that will never have a switch connected to it automatically transition to a forwarding state. So, what does this really mean? I mean, let's take a step back from our lecture, and what does this truly mean? So, if you've ever turned on a switched network where all the switches are brand new or have nothing in memory, and you turn them on, the switches don't immediately start working. It has to go through a process. You can also notice this when you start a packet tracer lab and everything is showing orange. And then slowly, within the first 15 seconds, you start seeing all the switch links go green. Because again, they're going through this election process, electing the root bridge, electing the root ports, well, designating the root ports, designating the discard ports, the alternate ports, designating the designated ports, designating the edge ports, and it does this within the first 10 to 15 seconds of the switch being powered on. Because again, it's going through those 5 learned port states. But if you had a way to tell edge ports to automatically not go through this process, just transition on, which we do, that's going to be the PortFast command, that allows the switches to be able to learn or start a little quicker. So there's different types of link types. So link types can be determined whether the port can immediately transition to a forwarding state. Edge ports obviously turn on. edge ports connected to a point-to-point connection are candidates for that rapid transitions to that forwarding state. Not all ports are capable of automatically going to a forwarding state. Let's talk about how do we configure our STP. So first of all, we have to make sure that STP is turned on. So we're looking at a Catalyst 2960 and the default configuration. So the feature, the enabled state, is enabled by default on VLAN 1. If you turn on spanning tree modes, you have PVST plus, where rapid PVST plus and MST plus are disabled by default. The switch's priority by default will be 32768. The spanning tree priority per interface is going to be 128. Again, these are the defaults. The default costs for a gigabit link is 4. For a 100 megabit connection, it's 19. And for a 10 megabit connection, it's 100. If we're looking at the default spanning tree VLAN port priority, again, it's going to be same as the per interface, which will be 128. The costs per VLAN per link, same link, gigabit, 100 megabit, 10. It's going to be that still the default 4, 19, and 100. Lastly are going to be the timers. Hello timer is going to be 2 seconds. Forwarding delay is going to be 15 seconds. Maxed age time 20 seconds. And the transmit hold will be 6 BPDU holds. All right, so now that we understand the defaults, let's look at how do we configure this. If you want to configure a specific switch to be a root bridge, you can do it a few different ways. You can actually set VLAN root primary, where root primary doesn't really adjust the priorities. It has a way to adjust the priorities of the bridge to be better one in the STP domain. So it does have the ability to manipulate the priorities to a degree, but not a whole lot. Here in method 2, we could also change the priority to a lower number. Or we can actually set, again, a root primary or a root secondary, and that will then set those as primary, secondary roots. If we want to verify, we could do a show spanning tree, and that will show which is the root bridge or the MAC address of the root bridge. You'll show things like the priority, the bridge ID, the MAC address, the hello timers, all of that. The forwarding states, the states and the costs. Here we're going to have the states, they're going to be the forwarding states. But if they're the blocking mode or anything like that, the states will be showing it there. So PortFast and BPDU guards. Oh, sorry about that. I was getting ready to sneeze. So when we set PortFast on an individual port, issuing again this spanning -tree PortFast, that will transition a port from blocking to forward immediately. It automatically puts those ports in a forwarding. We can also do what's called spanning tree BPDU guard, and we can enable it or disable it. And that guard puts the port in an error disabled state if it receives a BPDU. Because again, what we can do is on those edge ports that never should be connecting to a switch port, those ports should never get a bridge port datagram. So if we do the BPDU guard and we turn it on, if it ever is connected to another switch, it will turn off those ports. Do you start seeing how, if you don't truly understand how STP works, how having switches and links in your network automatically turn on and turn off could be kind of concerning. Apparently we don't want to go to the next slide. There we go. Per VLAN spanning tree, it does the ability to do load balancing, so we can actually do root bridges off of different VLANs. That way, here we have the root bridge for VLAN 20 on S3. We have a secondary root bridge for VLAN 20 on switch 1. We also then have switch 1 being the primary for VLAN 10 and the secondary on switch 3. That way we have a way to load balance these root bridges on different switches. That way, switch 1 does not have to be the root bridge for all VLANs. So another way is, again, you can change the priority. If we actually want to see spanning tree activity, again, issue a show spanning tree. Probably question mark so you can see all the appropriate subcommands. Here we're using the active one, and you can actually see the active MAC address with the priority, with the root ID and bridge ID. We're going to start talking about how we can start tracing down the root bridge based off of things like the bridge ID and root ID. That way, if you're not sure what switch actually has is the root bridge, we can start tracking it down. Load balancing, again, you can manipulate per VLAN priorities. So again, how do we do a rapid PVST basic configuration? We can global configuration mode, turn on rapid PVST, go to the interface. Once you're at the interface, spanning tree, link type, if it's point to point, and then that's it. That will set up basic rapid PVST on a device. How do we clear the spanning tree detected protocols? We can do that by typing in the command in the global configuration mode, clear spanning -tree detect -protocols. That will clear all detected STP configurations. Sorry, that will clear all detected STP protocols. So let's talk about the analyzing of the STP topology. You can do things like show CDP. You can use the information from that and the appropriate show spanning tree commands so that you can slowly start figuring out the root bridge so that you could verify the root bridge. Here we have two switches. So is this the expected topology versus the actual topology? This is where it gets interesting. A lot of people don't understand STP, so they turn it off because STP turns off ports. That's because they get in this issue of expected topology versus the actual topology. Why are these ports being blocked? And that gets into the question of, well, what are the path costs? And if you don't understand the path cost, you don't understand why those links are being turned off. If this guy is the root bridge, S3 has two links there. Well, why would we take 2 hops to get to switch 1? It's easier to turn off that port and forward everything out one link. Same thing here. Why would switch 4 want to do 2 hops when they can just do one? That's why that port gets turned off. By do show spanning tree and the appropriate interfaces, you can see which ones are in forwarding states and which one is in designate, or root roles. Here we're looking at switch 1. if we're looking at the appropriate units here, they should all be designated ports. So why is this one showing root and it's in a forwarding state? I actually have to see the configuration to kind of discuss that port more. So STP erroneous errors, very common. So failure consequences. So if this is a traditional loop and there's just one blocking state, here's a giant loop right here. So you have to be able to turn off those ports. If not, this is what ends up happening, and it's just, again, a large broadcast storm. So repairing a spanning tree problem. So one way to correct a spanning tree failure is to manually remove the redundant links. Physically remove the links. Before restoring that redundant link, determine the corrected cause of the spanning tree failure so we can look at it. In all honesty, a big part of this is typically a failure in understanding actual versus logical spanning tree. Normally what I do is I draw out spanning tree, I do my bridge priorities, and I should be able to see the links that I want to be turned off, which one will be designated ports, which will be root ports, which will be non-designated ports. I mean, you have to have an understanding of that technology to be able to do that. Once you're able to do that, you should not have spanning tree errors or problems because, again, you've mapped them out. So your actual would be what you're actually be getting. All right, let's move into one of our last major topics. First, hop redundancy protocols. So what happens when we have one gateway? So if the default gateway cannot be reached, the local device is unable to send packets off of that network. So what do? So even if there's a redundant router that exists that could serve as that default gateway, that segment, there is no dynamic method to be able to do it because we have one IP address that is our default gateway. So what we can do is we can actually have two routers, two layer 3 devices, and a virtual IP. So multiple routers are configured to work together so that they'll have the illusion of a single router. That's that virtual IP. So you could have two routers that are like an active and a standby mode. And for example, we have this guy masked as our default gateway. But in reality, it's a virtual router. They both have the IP address. But because this one is the active router, it's going to control this virtual IP. If this router goes down, this guy, the standby router, will go active and then take over control of that virtual IP. That way, we're always sending data to our virtual IP, which will be that default gateway. Thus, there should always be a path out. We already talked about that link failure, thus it failing over to the new forwarding router or the new active router. First hop protocols, HSRP, virtual routing redundancy protocols, or gateway load balancing protocols, GLBP. HSRP is a very common one, though you may run into VRRP and GLBD or GLBP in other areas. Notice I did not really talk about IRDP. That one is not as common. HSRP has been the one that I've actively used the most. They will do it in groups, again, active and standby. And you would actually do a configuration so that each one will be programmed with a virtual IP as well as an active IP. The active IP is the actual physical IP or the actual IP of the device. The secondary or the virtual IP would be of that virtual IP or that virtual router, so that they both understand that they both are that virtual IP. It's that the active one will process it. So if the active one goes down, the standby becomes active and it will process it. Show standby, you'll be able to see the groups, their virtual IP address, the state changes, and the virtual MAC address. GLBP is very similar, Cisco proprietary, but it does allow for load balancing. Also works as a virtual IP. Also works in groups. And that's actually the end of this chapter. We talked about many things, heavily STP, and a little bit about HSRP, a little bit about the different first hop redundancy protocols. That's kind of to get your feet wet. We'll go more in depth in later chapters. I want to thank you, and if you have any questions, please let me know.